Okay, so we just went over the basic idea behind k-nearest neighbors regression and the big differences in terms of compute time, memory efficiency, and then statistical properties and capacity for k-nearest neighbors. The big difference between that and linear regression. So now let's code a little bit in Python. So I'm going to import our main packages, sklearn, NumPy, and pandas, and then some other visualizations. Okay, so I'm going to import the wine data set. And just to recall, the wine data set, and I'm importing it in a more efficient way this time using pandas. Generally, you want to use pandas IO when you can, because it's a very nice interface. And so just to recall, the wine data set, it has several variables and then one quality variable, and this quality variable is our response. The remainder are the predictor variables, and they're all numeric. So we can describe it, typically we want to do this to see if there's any missingness. Unfortunately, sklearn does a pretty poor job of handling missingness, and we have to deal with those separately. We can also see things like the variances, the empirical standard deviations will vary very wildly between the different predictors. So that's something to take note of. And so if we look at, so we're going to separate out the y and the x distributions, or the y and the x arrays, and then create a training test split. And we're going to reserve 33% for the test set. So let's just check to make sure this did something reasonable. If we look at the shape of the training x and the shape of the test x, then we have roughly 33% of the total number of samples are in the test set. About half of the total number of the samples in the training set are in the test set. Okay. So this is a good time to give you an exercise. So instead of going off on my own, I think you should sit down and try to implement all of this yourself. So the first thing we want to do, for ordinary least squares, scaling doesn't make a huge difference. It maybe for numerical issues, it can be helpful to scale very, but when you have wildly different variances. But we did see that we had different variances for the x variables. Now, if we think about what k-nearest neighbors does, it will compare 2 points based on their Euclidean distance, right? Which is a sum of the squared differences between the different components of x, between the different variables of x. And so say we took one of the variables and just multiplied all the values by 10. Then the distances would all be multiplied by 10 in that direction. So the square of the difference gets multiplied by 100. Okay? And so what ends up happening is that the differences in variances can have a huge impact on how we relatively weight each of the different dimensions in the x variable. And so you have to standardize if you're using k-nearest neighbors. You have to standardize because otherwise you're implicitly saying those variables with very high variance are going to matter a lot more than other variables that have low variance. Now you could do that. It would be a modeling choice. It would give you a different model. But typically that's not really the behavior that you want, that one dimension dominates all the rest of the dimensions when we calculate our Euclidean distance. So we have to scale it. Right? Now what we want to be doing is we want to make any sort of fit on the test data alone. It's typically poor form to use the training x's in when you're fitting any part of the pipeline for your data processing pipeline. And one way you can think about this is that you really want to create a system, depending on the application, but you might want to create a system that you could then deploy in the real world, that whatever happened during the fit method, that's now fixed in place, and then when you get a new sample for a new test sample, you can apply all the transforms and all of the predictions to that new test point, and then no internal states that were set during fit, such as coefficients or the way in which we standardize, none of those will change, typically will change as we apply our predict algorithm, the predict pipeline, to the new test point. And so the best way to ensure that you do that is just to never not touch the test data during the training procedure, right? And vice versa. Once you're done fitting and training, then you don't touch it again, and you apply your learning algorithm to the test data point. So this is important because the standard scaler has the fit method and the transform method. Just like linear regression had the fit and the predict method, this has fit and transform. And typically, so if you look at the documentation, you can fit this on the training data and then transform the test data using the fitted standard scaler. So once you have your fitted and transformed training X's, then I want you to fit the following models using the training data. So first of all, linear regression. We've already done this once. Just do it again. Then k-nearest neighbors for a large range of k. Remember, k is a tuning parameter, so you want to start at 1 and then have a large range. I think I set mine up to around 250 or so. And I do odd numbers of k. But you can choose whatever relatively large range you want. Now, because we're fitting different models, you want to create a bunch of different instances for the k-nearest neighbor, one for each k. And then you can store these trained models in a list, and then just wait for the testing part. Then once you have that, you should create a custom model class. So this is something that I did on my own. You know, if you are not feeling up to it, this is sort of like more like bonus points, but it sort of gives you an insight into what is going on in fit and predict, and gives you a good sense of why it's important to have separate fit and predict methods. But you can just base it on the k-nearest neighbors regressor object class. And the basic idea is this custom model is just going to select columns 1 and 10 from your data set. So you can just hard code 1 and 10, create a global variable that's this 1 and 10 list of the numbers 1 and 10. And then what this custom model class does is it fits, when you call fit on this class, so the interface looks just like k-neighbors regressor interface. When you call fit, then it will fit the k-nearest neighbors only on these 2 columns of X. So it subselects the 2 columns of X. And then also predict will call predict on this k-nearest neighbors regressor, but only using those 2 columns. So this is just a good exercise to get accustomed to the interface for these regression objects, for these regression classes in scikit-learn. And then we're going to use each model to predict the test data and calculate the mean square error. Right? So now that we're done with training, we've done all of these fits, we have a list of different models that have been trained already, and now you want to use each of them in turn to apply them to the test data and then calculate the mean square error. And you can use the metrics module to find mean square error. And then you want to plot this as a function of k for each k and n method, and compare this to linear regression. Okay, so at this moment, pause and try to do all of this. You can do it right in the Jupyter Notebook, and then unpause and see the solution. Okay, I'm going to move on. So hopefully you have some solutions to this exercise. And you shouldn't, this is of course honor system, so you shouldn't look at the remainder of the Jupyter Notebook when you're doing this. Okay. So so the first thing to do is to fit your standard scalar. So we're going to initialize a standard scalar, call it stand, and then we're going to fit it on the training x's, and then we're going to transform on the training x's using this. There's typically a fit transform method that does both of these in sequence, but I just wanted to show you what this is doing. So when you do fit, it calculates that mean and variance, and then transform is going to subtract off the mean and divide out by the variance of each component. So when you fit ordinary least squares and k-nearest neighbors, the basic idea is that we're going to initialize each of these models and set the appropriate parameters and then just fit, right? So this is only touching the training data at the moment. Notice the last thing we didn't touch any of the test data either. So this is all part of the one big training process. So if we do lr.fit, we fit our linear regressor that solves the normal equations, finds the betas, and then we're going to create a list of k-nearest neighbors, the models, and then we're going to initialize a range of k for the k and n's, and then we're going to go through each of these k for k-nearest neighbors and fit k-nearest neighbors regressor for that specific number of neighbors. So this is sort of computationally cumbersome, but the data set isn't huge, so this doesn't take too long. And then we just append that k and n object to our list of k and n's. Okay. So that fits ordinary least squares and k-nearest neighbors. So the third part, and yeah, if you look at this model, this is a list of trained models. So we can just go through these and use predict on all these trained models. This is the nice thing about how these all have the same interface, is that I really don't have to, when I'm doing predict, I don't have to distinguish between what is linear regression, which is the k and n. They all have the same predict interface. That's the nice thing about it all being wrapped in one big package, like sklearn. Okay, so I'm going to create a custom line predictor class. This could be more cleanly done with using class inheritance, but that seemed to be a little outside of the bounds of what we're doing right now, and maybe your Python chops are not up to snuff yet. So we're going to create a global variable, which is the columns to select. I said it was 1 and 10, and then we're going to create the wine predictor class. And it's important to think of this as a class because now we're going to treat it, we're going to use it in exactly the same way we use k and n and ordinary least squares. Right? So what it does is when we initialize an object from this class, and if you're not accustomed to Python, this dunder init dunder, this is how things get overloaded in Python. This is how operations and methods get overloaded in Python, is through these dunders, double underscore. So what happens when we initialize the wine predictor class, we have to specify the number of neighbors if we don't want it to be the default 5. Then it's going to create a new k and n regressor class with the number of neighbors. But now when we call fit on the training and test, the training x and y's, then it's just going to subselect this selected columns and then call fit from the k and n object that's attached to this thing. Then when we want to call predict, it also selects the columns for the test x and then spits out the prediction from the KNN object. So it's just sub-selecting the columns 1 and 10 whenever we do fit and predict. Okay, so now moving on to number 4, we're going to predict with all of these methods, or actually, sorry, this is still number 3. We're going to fit for every k in our k-nearest neighbors. We're going to fit this wine predictor object. We're going to create it and fit it, and then append that to the existing models. Now we're on to the testing phase. So now we can start to touch the x tests, but we don't want to touch the y's because that would be cheating. So we need to apply our standardization transform to the x tests to put them on the same footing as the training data. And then we're going to go through all of these models. So, the first model is ordinary least squares, the next several, the next many are KNNs, the next many after that are the custom class that we defined in problem 3. And we're just going to make the predictions and then apply our mean square error metric to this and append that to the MSEs. So we're just going to get mean square errors for every model in our list. Now the nice thing is that because they all have the same API, they all have this predict method, and we can apply them uniformly in the same way to the test data set. Okay, so now I'm going to plot the mean square error. So this is the test error. This is the average of the test losses, the square error losses for test. And first of all, ordinary least squares, it's just a single number. There's no tuning parameter, so we're just going to draw it as a line here. And then if we apply k-nearest neighbors, it starts at k equals 1. It starts relatively high at an MSE of 0.6 or so. Then it drops down until it gets pretty close to the performance of ordinary least squares, with k being around 20, and then it goes back up. Right? For the wine prediction class, it actually starts really high. This MSE is almost higher than the variance. It might be higher than the variance of the y's on the test set. And then it dips down, and then it slowly starts to increase, but it maxes out at k above 50 and significantly worse MSE than ordinary least squares. So comparing these, I would say that ordinary least squares is doing the best when we compare these test errors. Now, one caveat is that typically when we tune these Ks, there is some fear that because we've fit many different models on the test data set, so there's a lot of models here, that the error that I'm reporting here, this error, say the minimum k-nearest neighbors error, this is actually artificially small. And this is for the same reason that that we do a training test split, is that when we are selecting our tuning parameters and when we're selecting our model, we want to evaluate our performance using a holdout set, this test set, right? But then if we want to say that our expected MSE on our test set is this smallest one of the models that we selected, that might not actually be that's no longer an unbiased estimate of our true risk, because we've selected from many models. So typically what we do, if we have enough data, is we also have an additional validation set in addition to a test set. So you can think of this as a validation set, which is allowing us to choose between our models. Then once we have our chosen, this is sometimes called model selection bias. Once we have our selected model, if we want an unbiased estimate of our risk, we then apply it to a separate held out test set. So you can think of this test set that I've constructed here as a validation set. And then if I want to give you an unbiased estimate of the risk, I would have to have a third data set that I've held out, so a second test set. So it's typical to do training validation test set splits. You can think of what I'm showing you here as my validation error. And to get an unbiased estimate of the true risk, I would need a second test set. And then I would apply, say, ordinary least squares fitted on both the training and validation on that second holdout.